Hi everyone. In this video I'm going to talk about substitution in square planar complexes. Recall from our previous discussions that metals that tend toward the square planar geometry are D8 metals, particularly when they're in strong fields. So second and third row transition metals that are D8, such as rhodium-1 and platinum-2, or palladium-2 and gold-3, really favor these types of geometries. Mechanism for substitution in these types of complexes tend to be associative in nature. So in other words, you're going to have interchange associative or purely associative type mechanism for the ligand substitution. The evidence for this comes from a strong dependence of the rate of the substitution on bond formation to the incoming ligand. In other words, the incoming ligand Y is going to have a strong influence on the rate of the substitution reaction. So this will occur whether the mechanism is purely associative and leads to the formation of an intermediate with a higher coordination number due to the bond formation between the metal and the incoming ligand Y, or in the case of an interchange associative mechanism where we don't have an intermediate but still bond the beginning or starting the bond formation between the metal and the incoming ligand Y is important in this transition state structure. Both the identity and the concentration of the incoming ligand will have an influence on the reaction rate. Additional evidence comes from the fact that these tend to have large negative entropies of activation and large negative volumes of activation. And then finally, we'll also at the end of the video talk about the strong dependence of the reaction rate on the trans ligand. That is the ligand in this position, which is trans to the leaving group X. And in fact, the leaving group X itself also has a strong influence on the rate of substitution reaction in these complexes. Now let's talk about the mechanism for substitution in these types of complexes. Shown here is a square planar complex with two generic ligands L. The leaving group is X, and the ligand trans to that leaving group is called T. We have the incoming ligand Y, which attacks at the metal center, as shown. This leads to a trigonal bipyramid intermediate. So what happens is Y attacks the metal. The bond between the metal and the leaving group rotates downward so that we can have a lot of space for the trans ligand, the incoming ligand Y and X in a trigonal plane. And so we have a trigonal bipyramid intermediate. The L ligands are along the axial portion of that intermediate structure. In a second step, X dissociates and Y moves into position exactly in the place where the X leaving group occupied in the original structure. There's an alternative mechanism to this which involves solvent. Solvent attacks at the metal center to produce a similar trigonal bipyramid intermediate. In this case, solvent is involved in that coordination. Dissociation of the leaving group X produces a square planar complex with the solvent in the leaving group's original position. This is followed by attack of the incoming ligand Y at the metal center to form a second trigonal bipyramid intermediate with now the incoming ligand Y, the solvent, and the trans ligand forming the trigonal plane. And then dissociation of solvent leads to the final product. Notice that the final result for both pathways is this product in which the incoming ligand Y has substituted for X at the position originally occupied by X. To represent the top mechanism as an elementary one-step reaction, using platinum as our example, we have the complex + plus the incoming ligand Y in one step to form our product and the leaving group X. So in other words, this elementary reaction is this pathway. Of course, we're not showing the intermediate that's formed as we write out this reaction pathway. So this would be a one-step mechanism. The rate law for this mechanism, assuming a rate constant K, would be equal to K times the concentration of complex times the concentration of the incoming ligand Y. The second pathway is a two-step mechanism. And in the first step, we have the original complex plus the solvent to form our new complex with solvent in the coordination sphere and X dissociated. So in other words, that's representing from here to here. And then in a second step in the mechanism, we have this complex plus Y go to form the final product with Y in the coordination sphere and the solvent now dissociated. If we add up these two, of course, you will get the final reaction because the solvent cancels out in both reactions. Representing the top elementary step in our mechanism with the rate constant K, and assuming that the second step is very fast, so in other words, this first step in our mechanism is rate limiting, we would get a rate law for this second mechanism equal to the rate constant K times the concentration of the complex times the concentration of the solvent. But of course, solvent is usually very large excess compared to the concentration of the complex or even Y, and therefore that is going to be subsumed by our rate constant K, which simplifies our rate equation as shown. So in other words, this pathway has what you would expect for a typical second order type of rate equation, whereas the one with solvent involved looks more like a first order process. We're going to label K in the two-step mechanism as K1 and in the one-step pathway as K2, so we can distinguish those two rate constants. Therefore, if we are measuring the actual rate of reaction for this type of substitution, we might be looking at the change in complex concentration over time. The actual rate equation we would observe would be a combination of both pathways because they wouldn't be able to be separated. So our final rate law would be equal to K1 times the concentration of the complex plus K2 times the concentration of complex times the concentration of the incoming ligand. Okay, so now let's talk about how we can determine the values for the rate constant K2 and K1 in these types of substitution reactions, as well as what is the dependence of the rate of these reactions on the incoming ligand Y. What you do is set up the reaction, several reactions, under pseudo first order conditions. In other words, conditions where the concentration of Y in the reaction is very large. And so under these types of conditions, this rate equation simplifies. Your rate equation simplifies to a K observed times the concentration of the complex. In other words, our concentration of Y is so large that it sort of becomes subsumed with our rate constant K, and so this equation simplifies to a K observed times the concentration of the complex. Under these conditions, the K observed is equal to K1 plus K2 times the concentration of the incoming ligand. So under these conditions of excess, we can plot K observed versus concentration of Y, always in excess, but we keep making that concentration larger and larger. Then we plot K observed versus concentration of increasing concentration of Y. We should observe a straight line dependence, a linear correlation between K observed and Y, as shown here. The slope of that line will be equal to K2, the rate constant for our one-step process, and the intercept will be equal to K1, the rate constant for the rate limiting step in the solvent-assisted process. Notice that the rate is shown to be dependent on the concentration of incoming ligand Y, right? As we increase concentration of Y, the rate is going up. In addition, we see that the rate is also dependent on the identity of Y. Notice the slope is increased when we switch from our incoming ligand being iodide to thiocyanate. There is a trend in the types of incoming ligands and the overall reaction rate for substitution. We see that as ligands become stronger sigma donors and as they get better at being pi acceptors, the rate of the reaction with the particular ligand increases. This is referred to as the ligand nucleophilicity. So what we're seeing is what is observed order. In other words, the increasing ligand nucleophilicity of these ligands with these types of metal centers. This should make sense because, as you'll see, the ligands with the faster reaction rates are softer ligands, and most of these metal centers include soft metals such as platinum. Okay, so next we're going to talk about the quantification of ligand nucleophilicity, and this is so quantifying, putting numbers to the increasing nucleophilicity of these various ligands towards a square planar complex such as this platinum complex shown. We use the nucleophilicity parameter eta to represent the nucleophilicity of these ligands, and the metal to which these ligands are attacking is listed as a subscript. So in this case, eta platinum. Eta platinum is going to be the log of K2, the rate constant for a given ligand, L. So for instance, the rate constant for substitution when cyanide is the attacking ligand at platinum, over K prime, K2 prime, which is the rate constant for our sort of standard or weakest ligand, which is methanol. So the log of the ratio of any given ligand rate constant over our standard, which is K2 prime, which is that of methanol, which is going to be sort of the most sluggish ligand to attack in a reaction, a substitution reaction at this soft platinum center. Based on this definition, the nucleophilicity parameter for methanol ends up being 0 because by definition you'd be taking the log of K2 prime over K2 prime, which would be 1, and the log of 1 is 0. So you'd get our lowest sort of standard for methanol, the eta platinum would be 0. Now, we also have a measure of the susceptibility of a complex to the nucleophilicity of the incoming ligands, and that's called the nucleophilic discrimination factor S. So S is a measure of the sensitivity of a given complex to the nucleophilicity parameter. In other words, what that means is that, for instance, as the metal center gets softer, we might expect them to be more sensitive, right, to increasing nucleophilicity or increasing soft character of the incoming ligands. The relationship between all these parameters is given here. If we rearrange this equation, we get log K2 is equal to our nucleophilicity parameter plus log K2 prime. And for a given, if we do this for a various metal centers, then they're each going to be modified by S. And you can see this looks like a linear equation. Plotting log of K2 versus the nucleophilicity parameter eta for a given ligand set, for a given set of ligands results in a straight line, right? But notice that the slope of the line is different for these two different platinum complexes. So the platinum complex with 2 chlorines and the ethylene diamine has a shallower slope, right, than the platinum complex with the 2 chlorides and the phosphine ligands. So phosphines are softer ligands. They are going to make the whole complex a little bit softer. And so now, notice the slope is steeper for that complex. In other words, it's more sensitive to changes in the nucleophilicity of the incoming ligands for this particular complex. So when we're analyzing this particular plot, what we see is, of course, the change in the rate, right, log of K2, as we change the ligands, and that follows the nucleophilicity parameter that we have measured. In addition, the sensitivity of a particular complex is represented by the slope, which is the nucleophilic discrimination factor S. So the slope of these lines are the S values for a given complex. Okay, so up to this point, we have talked about the role of the incoming ligand Y on the rate of this overall process. Right, so we focused on the nucleophilicity of Y and its effect on this incoming ligand on the reaction rate. It also turns out that the trans ligand T, shown here, so trans to our leaving group, also has a significant effect on the overall rate. So the identity of that trans ligand really has a significant contribution to the rate. And there's a standard pattern that we observe with varying the identity of that ligand T, shown here. So basically, the observation is that the rate of substitution increases as it's increasing in this direction, right? From water being the most sluggish trans ligand to carbon monoxide and cyanide being the most effective trans ligands at increasing the rate of the reaction. And what we see is that basically the pattern here is that as your trans ligands become better sigma donors and pi acceptors, you see an increase in the rate of ligand substitution. So how is this trans ligand having an effect on that rate? Well, the overall effect is called the trans effect, and it's from 2 combinations. One is the sigma donation properties of the ligands, and the other is the pi acceptor properties of the ligands. So we're going to talk about the effect of the trans ligand on this rate. So the first effect, imagine you have a metal center and a square planar complex like this. This orbital represents the dx squared minus y squared orbital, right? Which is aligned along, right, where our ligands are being directed, both the 2 sort of extra ligands. We're not too worried about these in this drawing, but our trans ligand and the leaving group, they're all donating into this dx squared minus y squared orbital. So as that trans ligand dumps electron density into that orbital, you get right there, it's dumping that electron density into the same orbital that our leaving group ligand X is using. So as we increase the donating power of the trans ligand, it actually weakens the bond to our leaving group X. And of course, since that is a part of what we need to do in order to have the reaction, right, as we go through our transition states, X has to leave. The fact that if our trans ligand is a good sigma donor, weakens this bond, it makes it easier for us to then break that bond and going from our reactant to the product. This sigma donor effect is called the trans influence. Now, to illustrate the effect of pi bonding, we want to redraw this intermediate so we can display the orientation in a way that's going to help us see the orbitals a little better. So I'm rewriting this complex, which is sort of on its side right now, right? The axial ligands are pointed this way, and we can see the triangle base here. I'm rewriting it so the ligands are up and down, and there's my triangular base right here. There we go. And then what I'm going to do is imagine yourself looking straight down from the top of this complex. So I'm going to look exactly straight down on top of the triangle, like that. Okay? So I've left out the L ligands, right? Because they'd be on top and bottom, so we can see this a little better. I've left them out. So we're looking at a top view here. Now, I put XY coordinate system on top of the metal so we can envision where the orbitals are going to be. So here would be, say for instance, this would be the dxy orbital on the metal. Notice, right, in that dxy orbital, we have a significant contribution of the ligand, the incoming ligand Y, donating electron density into that orbital, right? As it's doing that, it's increasing electron density on the metal. So again, electron density from the ligand Y, the incoming ligand, is being directed at the metal. Now remember, you're going from a 4-coordinate complex to a 5-coordinate complex in our intermediate. So we have 4 ligands dumping electron density in the metal to 5 ligands dumping electron density in the metal. So we're getting a lot of increased electron density at the metal. And in particular with this particular intermediate, that electron density is going into this dxy orbital. Now, if my transligand, though, here is a good pi acceptor, so increasing electron density at that metal, right, in the intermediate, if I have T, the transligand, is a pi acceptor, like a phosphine or cyanide or carbon monoxide, it can stabilize this increasing negative charge that's now being directed at our metal center, right, as we go from our reactant to our intermediate. Why? Because a pi acceptor has an empty pi star orbital, and remember, it can back bond electron density from the metal into itself. So, right, so we have, of course, electron density being donated from Y. That's increasing donation on the metal as we go to the intermediate. But that electron density, right, that buildup of electron density, right, can be stabilized by back bonding from that very same orbital into our trans ligand if it's a pi acceptor. So we have two parts to the trans effect, right? The first is strong sigma donors help in the trans influence, which weakens the bond to our leaving group. And then we have the pi acceptors, which help to back bond electron density, right? In other words, stabilize the increasing electron density that's building up on the metal as the incoming ligand Y comes in and attacks at the metal.